Today's lesson is on scientific notation with addition and subtraction. So as a reminder, scientific notation is that notation where we have a number between 1 and 10, like 3 and 7/10, multiplied by 10 to some power. And we use this to make it a little more efficient to add, subtract, multiply, divide very, very large numbers. When we talk about adding and subtracting with scientific notation, we're going to be combining and taking away very, very large and very, very small numbers. For example, 8 and 6/10 multiplied by 10 to the 4th, and 9 and 2/10 multiplied by 10 to the 5th. We always have the option to write out these numbers in standard form to add and subtract them. But today's lesson is going to be how to add and subtract a little more efficiently without having to convert the numbers to standard form. Let's refresh what we know about the distributive property. Let's say that we have 3 times the sum of x plus 7. The distributive property states that we can multiply this outside number, the 3 that's being multiplied by the sum, by each term individually, and then add them together to give us the same answer. So this is equivalent to this. The distributive property also teaches us that we can factor numbers. For example, if we started with 3x plus 3 times 7, we could pull out that common factor of 3 and multiply it by the sum of x and 7. This strategy is what we're going to use in our scientific notation problems. You'll notice here we have a common factor of 10 to the 9th power. So I know that I'm going to have the sum of 2 and 3/10 and 7 and 9/10 multiplied by the factor of 10 to the 9th. You guys are used to seeing it this way, where the common factor is pulled to the front. But since with scientific notation, we're starting out with the number between 1 and 10 multiplied by the power of 10, I'm pulling the power of 10 to the back of the problem here. Now I can simplify 2 and 3/10 plus 7 and 9/10 to give me 10 and 2/10 multiplied by 10 to the 9th power. So the sum of this brings me to this. For our first example, we have 2 numbers written in scientific notation being added together. Let's factor out our common term. Our common term is 10 to the negative 8 power. That means that I'm going to end up with 2 numbers added together multiplied by 10 to the negative 8 power. And those 2 numbers are what was multiplied by 10 to the negative 8 to start. 2 and 3/10 and 7 and 9/10. When I add them together, I end up with 10 and 2/10 multiplied by 10 to the negative 8 power as my final answer. Example 2, we're going to use the same strategy of factoring. However, we don't yet have a common denominator. Come over to the side for a second, and let's remember that when we have 3 times 10 to the 5th, that's equivalent to 30 times 10 to the 4th, or 300 times 10 to the 3rd, or 3,000 times 10 squared. Although the only one written in scientific notation is the single digit, the number between 1 and 10 multiplied by the power, all of them are mathematically accurate and they equal to 300,000. Let's use this to make this problem easier. So for example, we have 2 and 3/10 times 10 to the 7th and 7 and 9/10 times 10 to the 8th. I'm going to take this term and make it to where it's multiplied by 10 to the 7th. And in order to do that, my decimal has to move 1 time. I get 79 times 10 to the 7th and I bring down the term that I haven't changed. Now I have my common factor of 10 to the 7th power. I factor that out, and I fill in the two terms that are added together, 2 3/10 and 79. When I add them this time, I line up my decimals and I end up with 81 3/10 multiplied by 10 to the 7th. If we're writing it in accurate scientific notation, I move the decimal and convert the 7 to an 8, giving me my final answer of 8 13/100 multiplied by 10 to the 8th power. Let's walk back through this problem. First, I noticed that I don't have a common factor, but I could get one by converting 10 to the 8th power to 10 to the 7th. In order to convert 10 to the 8th to 10 to the 7th, I have to keep it equivalent by moving that decimal in the 7.9. Now I pulled out my common factor, and then I converted my final answer to scientific notation. Example 3, 2 3/10 times 10 to the 2nd power, plus 7 9/10 times 10 to the 4th. I need them to have those common powers of 10. So I'm going to convert the 7 9/10 times 10 to the 4th power to a number times 10 to the 2nd power. Since I'm changing that to a 2, I need to, and I changed it by 2, I need to move my decimal 2 places, giving me 790 times 10 to the 2nd power. Now that I have those common powers of 10, I can factor that out to 10 to the 2nd and add the 2 3/10 with the 790. That gives me 792.3 times 10 squared. But since that's not technically written in scientific notation, I move my decimal twice, and this becomes 10 to the 4th power. Final answer, 7 923 thousandths times 10 to the 4th power. Here's one for you to try. Pause the video, try on your own, and then play to check your answer. Ready? I'm going to convert the 8 times 10 to the negative 4th to be multiplied by 10 to the negative 3rd. Since I'm adding 1 to this power, I have to take 1 away from this, bringing me to 0.8 times 10 to the negative 3rd. That gets added to 3 times 10 to the negative 3rd power. I can then factor the 10 to the negative 3rd out and add the 3 and the 8/10, giving me 3 8/10 times 10 to the negative 3rd power.